Hi everyone. Now let us solve question number 6 from exercise 12.1. Question goes like this. Minimize z is equal to x plus 2y subject to constraints 2x plus y greater than or equal to 3, x plus 2y greater than or equal to 6 and x and y greater than or equal to 0. Let us have a look at the solution. So the objective function given is z is equal to x plus 2y. Constraints, the two constraints given below, what you see in the rectangular boxes, these are particularly given for this problem. Now what you see in the circle here is a general constraint or a set of constraints that is common for all the problems of the chapter, x and y being non-negative. But what is special here is, if you just observe, we will see that the objective function z as well as the second constraint in the second rectangular box are same, x plus 2y. There is something common in them, right? We will see how special that is in the solution at the end. So let us have the first constraint, that is 2x plus y, which is greater than or equal to 3. We will first consider the inequality as an equation so that we can find out the boundary line. It's a common step. We have been doing this all along. So first we will try to find out the y-intercept by substituting x equal to 0. You can see that y becomes 3, and similarly we will substitute y is equal to 0 to get the x-intercept, that is x is equal to 3 upon 2, which is also equal to 1.5. So we get 2 points according to the tabular column here, that is 0, 3 and 1.5, 0. So we got 2 points on the first first inequality, which we will convert it as an equation. Next we get the second inequality, which I already mentioned that it is very similar to the objective function. Now we consider it as an equation first to get the boundary line there. So substituting x equal to 0, we get y equal to 3. Similarly, substituting y equal to 0, we get x is equal to 6. Hence, from the tabular column, it is clear that we have 2 more points here, 0, 3 and 6, 0. Now, since we have got, so we get 2 points from the first inequality, that is a and b, and 2 more points from the second inequality, c and d. When we plot the graph, we find that the 2 points from 2 different inequalities, that is a and c, they coincide at the same place, that is 0, 3. And when we shade the area, the region, to find out the feasible region, we find that the origin 0, 0 does not satisfy both the inequalities. This shows that the region containing the origin should not be chosen. We choose exactly the opposite region. See, for one of the lines, that is 2x plus y equal to 3, if you concentrate on the graph there, see O or the origin is on the left lower side. Hence we will not consider that area. We will consider the opposite area, that is the area on the right upper corner, right upper side. Similarly, if you look at the line x plus 2y is equal to 6, again here also the inequality, if you consider, it does not satisfy the point O, that is origin. Hence we again choose the side which is onto the right upper side. The common region will be the region that is seen in pink in this diagram. So we come to see only 2 corner points here, that is, one is at A or C, whichever you want you can take, that is 0, 3. Another point is D, which is 6, 0. These are the only 2 corner points that will be considered. So hence let us try to find out the value for objective function. Now in the table you can see in the first part, that is point A is taken as 0, 3, where 0 is x value, 3 is y value. We substitute that in z. So z becomes 0 plus 2 into 3, that is 6. So z value is 6. In the second case, where D is the corner point, it is 6, 0. We substitute that in z, equation z, that is z is equal to 6 plus 2 into 0, where 6 is x value and 0 is y value. We get final answer again as 6. Since both the values at the corner points are 6, we will have to consider 6 itself as the optimal value. But on further inspection, we also find that, see, the value z is equal to x plus 2y is a line, and throughout that line z value will remain 6. For example, if you consider another point 2 comma 2 which also lies on the same point, x you substitute 2 and y you substitute 2, we will again find out that 2 plus 2 into 2, that is answer 2 plus 4, which is equal to 6. Again z value will become 6. So throughout this line the value is remaining 6. Also, another thing to look at is the feasible region is unbounded. We had a similar situation in question number 4, that the region was unbounded. In this case, what we do is we substitute the present minimum value, which is 6, into the objective function. So in the objective function z is equal to x plus 2y, we consider it equal to 6. To find any value lesser than 6, we will consider the inequality, which is in bold there in the fourth line, z is equal to x plus 2y less than or equal to 6. When we try to plot the points which satisfy this inequality, we find the region in blue that we find in the picture. See, the region in blue represents all those points which will be lesser than 6, and the region in pink is the feasible region that we have got. Now we find that except for the line x plus 2y equal to 6, which is the coinciding line between blue and pink, there is no other intersecting area. From this we can conclude that the x plus 2y equal to 6 is the line which gives us the minimum value. Throughout the line the value of the function remains 6. Hence safely we can conclude that therefore the function z is equal to x plus 2y has a minimum value of 6 at every point on the line x plus 2y equal to 6. If you have missed any solutions so far, you could just click on the link that is available here. The playlist that is visible, you can click on that and you will find the solutions of all the remaining problems. Or you can do one thing is click on the notification for this channel and please subscribe, so that whenever a new solution is uploaded you will be notified. Thank you.